Have you ever built a tower out of blocks? You start with one simple block, then another, and another. Suddenly, with just one tiny nudge, the whole thing can come crashing down in a huge, complicated mess. That's a bit like what chaos theory is all about. It's the science of how very small, teeny tiny changes at the beginning of something can lead to enormous, wild, and totally surprising results later on. It shows us that even when things seem to be following simple rules, their future behavior can become incredibly complex and almost impossible to predict perfectly. It's not about things being messy in your room, it's about a hidden order within systems that look completely jumbled up. This amazing idea didn't just pop up overnight. It started a long time ago, way back in the late 1800s, with a brilliant thinker named Henri Poincaré. He was studying the movement of planets and stars, a system that people thought was as regular as a clock. But Poincaré discovered something startling. Even with just 3 celestial bodies, like the Sun, Earth, and the Moon, their paths could become so tangled and complicated that you could never perfectly predict where they would be far into the future. He realized that a tiny, almost immeasurable difference in their starting positions could lead to them being in completely different parts of the sky millions of years later. This was a huge deal. Then, many years later, in the 1960s, a meteorologist named Edward Lorenz accidentally stumbled upon this idea again, but this time with weather. He was using a very early computer to run a weather simulation, creating a simple model with just a few rules. One day, to save time, he restarted a simulation midway through by typing in the numbers from an earlier printout, but he rounded the numbers off just a tiny bit, from 0.506127 to 0.506. He thought such a minuscule change, smaller than a snowflake's whisper, wouldn't matter at all. But he was wrong. The new weather pattern started off the same, but soon it diverged wildly, creating a completely different forecast. This one tiny, seemingly insignificant change had created a totally different outcome. Lorenz realized that this sensitivity to initial conditions was a fundamental part of many natural systems. He had discovered the heart of chaos. It wasn't that the system was broken or that his computer had a bug, it was the nature of the system itself. This groundbreaking discovery showed that perfect, long-term weather prediction was likely impossible, not because our tools weren't good enough, but because the atmosphere itself is a chaotic system. His work opened up a whole new field of science, helping us understand countless things, from flowing water to the stock market. Edward Lorenz's discovery gave birth to one of the most famous ideas in all of science, the butterfly effect. He famously asked, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Now, this doesn't mean a single butterfly is a tiny tornado-making machine. It's a metaphor. It's a powerful way to explain the idea of sensitive dependence on initial conditions. It means that in a complex system like our planet's atmosphere, a very small change, as small as the gentle stir of air from a butterfly's wings, can create a tiny ripple that grows and grows. Over time, that tiny ripple can influence other ripples, which influence bigger movements of air, eventually changing the path of a major weather system. Let's think about it with a different example. Imagine you're playing a game of mini golf. You tap the ball just a little bit to the left of where you intended. For the first few inches, it looks like it's still heading for the hole, but then it hits a small pebble you didn't see. Because of that tiny initial error, the pebble sends it off at a slightly different angle. It then rolls down a ramp, bounces off a windmill blade, and ends up in the water hazard instead of the cup. A difference of less than a millimeter at the start led to a completely different result at the end. That's the butterfly effect in action. This principle isn't just for weather or games, it happens all the time. Think about a simple pinball machine. When you pull the plunger and launch the ball, its path seems wild and unpredictable. Even if you tried to launch it with the exact same force a second time, the tiniest difference in its starting position would cause it to hit the bumpers and spinners in a completely different sequence, leading to a wildly different score. The system follows the simple laws of physics, but its outcome is incredibly sensitive to that initial launch. That is the essence of chaos at play in our everyday lives. The butterfly effect teaches us a profound lesson about the world. It's a place where small actions can have big consequences. It doesn't mean we should be afraid to do anything for fear of causing a tornado. Instead, it helps us appreciate how interconnected everything is. It shows that in many systems, from ecosystems to our own lives, a small, positive change can also ripple outwards and lead to unexpectedly wonderful outcomes. It's a reminder that even the smallest details matter a great deal in the grand, complicated, and beautiful dance of the universe. Now, when you hear the word chaos, you might think of pure, unpredictable randomness, like rolling a die or static on a TV screen. But in science, chaos is something very different and much more interesting. Randomness has no pattern at all. It's complete disorder. Chaos, on the other hand, has a hidden order. A chaotic system follows strict deterministic rules. If you know the starting point exactly, you can figure out the next step. The problem, as we learned with the butterfly effect, is that you can never know the starting point with perfect, infinite precision. Chaos is deterministic, but it's completely unpredictable in the long run. To help visualize this hidden order within chaos, scientists use a cool concept called a strange attractor. Imagine dropping a leaf into a swirling stream. The leaf will never follow the exact same path twice, so its movement seems unpredictable. However, you know it will always stay within the banks of the stream and will generally move in a downstream direction. The overall pattern of the swirling water, the eddies and currents, is the attractor. A strange attractor is a mathematical picture of the path a chaotic system will follow. It's a complex, looping shape that shows all the possible states the system can be in, revealing a beautiful, intricate structure hidden within the chaos. Another amazing feature you find within chaotic systems is something called a fractal. A fractal is a pattern that is self-similar, which means it looks the same no matter how much you zoom in or out. Think of a snowflake. If you look at one of its 6 big arms, you'll see smaller branches coming off it. If you could zoom in on one of those smaller branches, you'd see even smaller branches that look just like the bigger ones. Nature is full of fractals. You can see them in the branching of trees, the jagged coastline of a country, the structure of a fern, or even the way lightning forks across the sky. Fractals and strange attractors are the visual language of chaos theory. They show us that underneath what appears to be a jumbled mess, there is often a stunning and infinitely complex pattern. They prove that chaos is not just noise, it is a system with deep structure. It's a new kind of order that is more dynamic and intricate than the simple, predictable order of a pendulum swinging back and forth. Understanding these concepts helps us see the hidden beauty in things that we might otherwise dismiss as merely messy or complicated. Chaos theory isn't just an abstract idea for scientists and mathematicians. It's all around us, influencing our world in countless ways every single day. The most classic example, of course, is weather forecasting. Thanks to our understanding of chaos, we know that predicting the exact weather 2 weeks from now is basically impossible. Forecasters now use ensemble forecasts, where they run many simulations at once, each with slightly different starting conditions. This gives them a range of possible outcomes, which is why you often hear a forecast that says there's a 40% chance of rain instead of a definite it will rain. But chaos shows up in many other places in nature too. Think about animal populations. The number of rabbits in a field can fluctuate wildly from year to year. A simple model might suggest a smooth, predictable cycle, but chaos theory shows that small changes, like a slightly harsher winter or a new predator moving in, can cause the population to boom or bust in ways that are very hard to predict. It's also present in ecosystems, where the delicate balance between different species is a chaotic dance. The removal of one tiny species can have cascading, unpredictable effects on the entire food web. Even your own body is a chaotic system. Your heartbeat, for example, isn't perfectly regular like a metronome. There are tiny, chaotic variations in the time between each beat. Doctors have found that a healthy heart exhibits this kind of mild chaos, while a heartbeat that is too regular or too random can be a sign of illness. It seems our bodies rely on this controlled chaos to be flexible and adapt to changing demands. Even something as simple as a dripping faucet can become chaotic, with the drips falling in a complex, non-repeating pattern. Ultimately, chaos theory gives us a new lens through which to see the world. It teaches us to have a little humility about what we can predict and control. It shows us that the universe is not just a simple clockwork machine, but a place of incredible complexity, creativity, and surprise. By understanding the principles of chaos, we can appreciate the hidden patterns in nature, build better models for complex systems, and recognize how interconnected everything truly is. It opens our minds to a world that is far more intricate, dynamic, and wonderfully unpredictable than we ever imagined. Consider the science.